Hello, this is Alexander Powell recording a video for Fluent Project 2. This project is about flow simulation around a 2D cylinder. The first instance here is going to be inviscid flow around a 1 meter diameter cylinder, and the rest will be the same 1 meter diameter cylinder, but that cylinder will now rotate at various speeds. First I want to show how I created my geometry. I already have Design Modeler open. So first what I did here is on the XY plane I sketched a circle right at the origin, and then I dimensioned it, and it's going to be 1 meter. We'll zoom in here. Alright. And then I created a surface from this sketch. And you want to make this a frozen surface. And now I'm going to do another sketch here, and this sketch is going to be the area where the airflow will occur. So I'll do a little rectangle here. Just going to dimension this. This guy, this guy. This guy, and this guy. So I made my rectangle here 8 by 10. Alright, now we have a rectangle here, and then we can do the same thing, create a surface from sketch. Same thing, we want to do frozen. Base object surface sketch 2. Pick. There we go. Generate. And you want to do add frozen so that the design modeler sees the rectangle and the circle here as two separate objects. Now after you do this, we can create a boolean, a subtraction boolean. We're going to do the second surface body as the target, and the first surface body as the tool. Generate. Now you see we have the cylinder cut out here from the surface, and that's going to simulate the 2D cylinder. Okay, so this is the geometry. So we can X out of here. Now that's the geometry I created over here. Now I'll show the mesh that I made for the geometry. So it opens up here. Now I shared this mesh across every instance of the simulation. Alright. So to create my mesh, I first created a mesh element size of 0.1 meters. Then I decided to do an all triangles method with this one body here selected. The all triangles method. Then I did edge sizing around the circle here, the cylinder. The same element size, 0.1 meter. And then afterwards, I did one more. I did an inflation in this same face here, but then I had the boundary to be the circular edge again. The first layer height is 0.01 meters, 50 maximum layers with a growth rate of 1. It creates a mesh like this. And then before I moved on to the Fluent simulation, I created name selections here. So the inlet is that edge, outlet's this edge, symmetry is the top and bottom edge, and then the wall is the cylinder. And that's the mesh there that was imported into each of these Fluent simulators. So I'm just going to go into the solution here so we can see the velocity and CP distributions as well as the drag and lift coefficients. So this here is the solution for the inviscid flow stationary cylinder. And I'll of course show how I set up this simulation. As it loads here. Alright, so this will load in. When you hit setup, I hit solution so I can already, it saved my results from when I ran it previously. But the screen all looks the same when you hit setup. So for this one, you want to come to models and you want to make sure you have viscous set to inviscid. Materials, you want to make sure you're at air at the density at sea level. And you want to come to your boundary conditions. The inlet, you want to make sure you're set to 5 meters per second for velocity magnitude. Outlet, you want to be at gauge pressure 0, and there aren't any really wall settings that you can mess with when you're in inviscid flow. Some of the things I did here is I created some report definitions. So you can do that by hitting new, force report, and I picked drag at the wall, and then I also created one for the lift coefficient there. CD is for the drag coefficient, CL is for the lift coefficient, and the lift coefficient is the same thing. You just hit leave lift coefficient selected, hit wall, and then you can hit OK and it'll add to it. I won't do it now since I already have mine saved. You can see that it monitors it here. And then you want to come to initialization, hybrid. Oh, I just initialized it again. Whoops. But you want to come to more settings and just make sure that's 10 or higher. Then you can run calculations. And I have a couple plots here. I have the CP graph. Save and plot this. So this is a pressure coefficient along the curve length. So along the surface of the wall there, it's going to go around the curve. You can see this. Make sure this is yep, and so this here is your pressure coefficient along the curve length of the wall here. Let me see if I can zoom this in a little. And then let's see the velocity one. And this here's the velocity one. Yeah, let me look at this one again. Yeah, so you see here the pressure coefficient doesn't have as much variation as the velocity variation does. We can even do total pressure. You can kind of see this here, but the pressure coefficient does not change that much along the curve length of the wall here. You can mess around with this and do direction vector, but again, there's no really difference. I made sure to pick curve length for all of my graphs along the inviscid and viscous. And then you can come here to the report definitions actually. So this is the drag force coefficient you compute, and that's what it computes it to, which should be 0 for a, that's very close to 0. But theoretically it's supposed to be 0. There should be no drag force in an inviscid flow. And then the lift coefficient here, we can compute this as well. Also very low. due to that flow. And so we can kind of get a better look at why these two values are so close to zero. There's not going to be any drag along that cylinder. And so if we actually come here to, oh, well, let me just update this. So I'll update the results here. It might thought I reinitialized it. The results that show up when I open it will be my most recent results. Alright. So let me open up the results here. And you can see here that the flow practically just goes around the cylinder almost like it wasn't there, so I just gotta avoid it. Hugs the cylinder wall, and there is no drag really. Theoretically, there should be none. I mean, we saw there that the drag and lift coefficients were not zero, but they're very close to zero. Theoretically, here at the top and bottom of the cylinder is when the velocity should be the fastest. It should be 2 times u infinity, and u infinity is 5 meters per second, and we see here that these red values correspond to 9.774, which is very close to 10 meters per second, which, so theoretically, that seems to check out. Yeah, so, and this is all for the inviscid one. Now for the rotating cylinders, I'm going to show just one example because the process is the same for all three of the rotating cylinders, except you'll just be changing the rotation speed on the wall. So let me close this out. And then let me close this out. Yep. So I'm going to do this. This is the case where circulation is equal to 4 pi times free stream velocity times the radius of the cylinder. So this is where it's supposed to be equal. So again, I'll come to solution first just so we can see the plots and the lift and drag coefficients. So normally potential flow, you're supposed to do this inviscid, but Fluent doesn't give the option to rotate the cylinder with an inviscid model. So I just set this to laminar, and then I just left the air settings be default. So we have the density at sea level and the viscosity at sea level. After that, everything else with regards to inlet velocity will be the same, and outlet pressure is gauged. So we have a 5 meters per second velocity magnitude, and now what it changes is you need to come to the wall settings here. And so I set the wall to be a moving wall. This is your only option here, no slip, absolute motion, rotational. And now I set the speed to negative 31.4159 radians per second. The negative sign is important. The flow is flowing from left to right. And so that means when it's flowing over the top of the cylinder, that flow is also it'll be making the cylinder, if the cylinder was spinning or if it was able to just freely rotate, that flow would be making it spin clockwise. So to make the streamlines look how they are in the project requirements, the cylinder needs to spin clockwise. So the negative is because Fluent treats negative as clockwise and positive as counterclockwise. So the cylinder is spinning clockwise 31.4159 radians per second. Now that's the circulation speed that is equal to 4 pi times the free stream velocity times the radius of the cylinder. So what this should give us is flow over the cylinder like this, and there should be a stagnation point at the very bottom of the cylinder. And that's theoretically for inviscid flow, velocity potential flow. So that's where it's supposed to be. Same thing. you just gotta add a drag coefficient and a lift coefficient report definition, like I showed in the Inviscid simulation. Then you just run the calculation. So I have some plots here now as well. Do the pressure coefficient, save and plot. This is what the pressure coefficient looks like at 31.4159 reigns per second wall rotational speed. This is what it looks like here. And then we have the velocity one. It looks like this. Peaks there at about 15.6 meters per second. The rest it's very, very small. Or it's about, there's not a lot of variation in the wall speed actually. But now the important part is going to be the streamlines. So we'll close this out. Well, before we do that, I'll also show the drag and lift coefficients for this. So we can compute this. You can see here the drag coefficient's 10.349562. And the lift coefficient is 229.65868. So yes, there's definitely a lot more drag than the Inviscid, because Inviscid should be 0, and a lot more lift as well. In terms of, well, not more lift, but a higher lift coefficient and a higher drag coefficient. So we can minimize this, come to results. So these are the streamlines over the cylinder, rotating at that circulation speed of negative 31.4159 radians per second. So you can see that it doesn't look like the stagnation point is right at the bottom of the cylinder, but it is close. And this is going to be due to, well, these cases here in the project are based off that potential flow of an Inviscid rotating cylinder, but Fluent can't actually simulate that because there's no drag, and these cases are all theoretical, but when it is trying to simulate this, it does get close to having that stagnation point right there at the bottom. This is just velocity streamline, so you can see here, velocity at the top is much higher than it was on the Inviscid. Well, not much higher, but it is higher by about 5 to 6 meters per second higher than the Inviscid case. If you look closely, you can kind of see there is flow. There's a, there's going to be like that certain flow, that speed. There's going to be some flow and some type of velocity around the entirety of the cylinder because it is rotating on its own, pulling that fluid with it due to the viscosity. But yeah, so this is one of the viscous simulators for rotating cylinder at the condition of circulation is equal to 4 pi free stream velocity times radius. And the other two, this one is going to be with circulation less than that value of negative 31.4159. And this one is going to be the case where circulation is greater than that 31.4159. Now, those streamlines and all that data will be included in the spreadsheet that I submit for the project. But I want to definitely go through the geometry, the mesh setup, the geometry setup, and the just a typical setup for the Inviscid simulation, and then the rotating simulation. These two have the same setup as this, and I'm only changing the wall rotational speed. Other than that, it's the exact same. So yeah, that's my Fluent project too. Thank you.